Is that invasive? There's always somebody. And now nobody officially. I could have logged on anonymously. One more minute. Okay, let us begin. We are officially online, so wait for the YouTube people. Hey, everybody. Which is you when you watch this later, so you're going to yourself. Except there's always somebody. I think it's Mateo's not here. He's always watching online. So hey, Mateo, we know you're not here. That's not awkward at all. Okay, so we have good news and bad news, and the good news is the bad news. Bad news for me, good news for you, and that is every year when I teach this class, I always reserve a couple of lectures for the TA to give a guest lecture or bring in some other experts. And I kind of forgot to arrange that this year, so we have one extra lecture, which means we have one fewer lecture. So I'll probably cancel the very last class or reserve it for a review session, right? If I did the math right, which is always questionable, right? Given I'm a stats prof, I did the math wrong. We'll find out, but don't be surprised if you get an email saying we have too many classes and one's going to be removed. Okay, is the audio working here on YouTube? Yes, it is. All right, so continuing on our wonderful topic from last time, which was ranked correlation. We mentioned that correlation is related to linear regression. So today we'll talk about linear regression. And how many of you have done linear regression in high school before? Really? Oh, it used to be standard back in the day. What's up with high school these days? All right. So linear regression is a pretty important topic. It's one of, amongst, if you could argue that it's an advanced technique, I don't think it is an advanced technique, but if you could argue that it is an advanced technique, it's one of the more useful advanced techniques you could apply in many aspects of your life. So I'm trying to take some famous examples recently. I had a colleague who accurately projected that India was missing X millions of girls, right? So there should be more girls than India there are. And he did so by projecting ahead from the census the number of expected female births in India today, and found there's a gap of about 3 or 4 million. And we assume that's due to selective abortion, etc. And that caused all kinds of international trouble. But he used a very simple technique called linear regression to make that prediction. I'm actually going to try to predict your final exam marks based upon last year's model from linear regression. So we can do all kinds of funny things. So in previous years, the first time I taught this class, I had a student volunteer. We decided to try to predict who would win that TV show, The Biggest Loser, where you try to lose a lot of weight. And for that, we use multiple regression, which is a kind of linear regression, and we'll talk about that 2 lectures from that. But essentially, all you do is you get a couple of seasons worth of data from the. You ever watch a TV show, Biggest Loser? It's a bunch of overweight people trying to lose weight, right? And whoever loses the most weight is the winner. I know, right? So, but there's a caveat to the game show, and that is they vote each other off the island. So there's that random variable, and they do that, I think, deliberately, so mathematicians can't predict the winner. Because otherwise, your starting weight and your gender and your socioeconomic status and your age, etc., I can probably accurately predict who's going to lose the most weight. So they throw in that random variable people are waiting to screw you up. So anyway, it's a powerful technique, and hopefully, if it intrigues you, you can use it in your life, maybe, possibly. Let's begin. So far, we have looked at 3 measurements of correlation. Now remember, correlation is when we try to figure out if there's a relationship between 2 continuous variables. So we looked at the Pearson's rule, which is the most common. It's when we have 2 integral ratio level variables, and it's a parametric test, meaning it's related to the distribution on a theoretical distribution. We looked at Spearman's rule, which is the rank equivalent of Pearson's rule. That's when we only care about the ranks of values, the order in which they come, not the actual values themselves. And we talked about Kendall's tau. Now, we didn't do Kendall's tau, but I want you to know that it exists. In practice, Kendall's tau is probably better, but again, we can't do it by hand. So that's why we're still stuck in the old paradigm of teaching these techniques, which you can do by hand. This is the formula for Spearman's rho, the ranked correlation coefficient. D is the differences in the ranks of each of others measures. And remember, Kendall's tau, again, we're not doing in this class. Now, here's a couple of scary faces. There's Legendre and Gauss. Gauss I mentioned before. Gauss, the father of mathematics, the greatest mathematician to ever live, probably. And I mention his name all the time because he's terrifyingly brilliant, probably an asshole. And history has shown that he probably discovered all the major algorithms and treatments of modern statistics and mathematics, even when he didn't publish them. So what often happens is some other mathematician, hey, look, I discovered it. Oh, I did that years ago. Yeah. So hence the asshole title. But both of these guys and some others independently developed a technique for looking at the motions of bodies around the sun. Don't write this stuff down. I'm not going to test you on the history of mathematics. Just to give you a little bit of flavor of why it exists. And it's from their analyses of trying to predict where planets and observations will be in the sky that we have the technique called regression today. And there are different types of regression. All regression means is from biology. It means characteristics of animals regress to a common characteristic. Or we have something in general science called regression to the mean. You heard that term before? Regression to the mean? That's when, let's say you're doing a study and you measure the fitness levels of 100 people. And you rank them from the most fit to the least fit. And then a week later, you decide to take the bottom 50 of the list, the least fit people, and retest them. What do you think will happen to their fitness levels? Will it be higher, lower, or stay the same? Nobody got to guess. Guessing's free. Who says higher? It will be higher. How about the top 50? If I retest them, will they be higher or lower, or the same? They'd be lower. That's right. Why do you say that? Obviously, you're guessing, but do you have any theories? Yeah, look at you being smart. Excellent. So, because extreme measures tend to be evened out over time, right? So, if you're extremely high, you'll probably come lower. If you're extremely low, you'll probably get higher. We regress to the mean. We regress to the middle. So, large animals over time, evolved to be shorter, and so forth, right? That was an old-fashioned observation. So this idea of regression popped out of biology into mathematics, where maybe we can take extreme observations, extreme behaviors, and figure out an average behavior that takes away the extremes and brings it down to a model that allows us to predict behavior. There are all kinds of different kinds of regressions. Today we're doing linear regression. Most commonly in epidemiology, we do something called logistic regression. That's where we try to predict which are the factors that are most associated with a dichotomous outcome. Like, will I go to the ER today or not if I've got flu, right? So we'll take all these data, people went to the ER and those who didn't, and we regress them down to a set of attributes. For example, if I'm male, I'm less likely to go to the ER. If I'm older, I'm more likely. If I have this income level, I'm this likely, etc. So regressions are very useful for creating models to make predictions. That's really the primary reason for doing it, to make predictions. And that's what makes it so exciting. So you can use, again, this in your regular life to make predictions. Maybe. We'll see. So, again, in statistics, regression means the process of individual observations being processed to make a model, and that model is used now to explain the universe and make predictions. The model can be any shape, but today we'll care about the linear model, hence linear regression. For example, will your marks of the midterm allow me to predict your marks on the final? Possibly, and it's probably a linear relationship, and we'll figure that out, what that means in a second. Okay, there's a strong link between correlation and regression. Because again, I can take the distribution of your midterm marks and I can correlate it with the distribution of your final marks from last year's class. So the strength of that correlation allows me to do the prediction of this year's class. So when I'm doing a regression, I need data from a previous incarnation, because I'm making a model based on previous experiences to make predictions about the current experience or the future experience. There are two kinds of linear regression. There's simple and there's multiple. Today we're going to look at simple. In this class, I'm not going to have you compute multiple regression, but you're going to have to diagnose some of its characteristics. So linear is what you possibly did in high school, those of you who were exposed to it, and multiple regression you probably have never seen before. So simple regression is like that. Creating essentially an equation that looks like that. Y equals alpha plus beta x. You may remember the straight line equation from high school. Y equals mx plus b. It's the same thing, except now we're in the grown-up class. You use Greek letters instead of human letters. Because Greek letters aren't human letters. I have a bad back right now, and I'm on all kinds of drugs. So, and this is a multiple regression equation. See, it's fairly, here's my pointer, here it is. It's more complicated, but this is just an element of that. See, that is the same as that. We're adding extra terms onto it. So multiple regression is just a complicated version of simple regression. Again, the straight line equation you learned in high school was y equals mx plus b. And when I learned this when I was God knows how young, I thought I'd seen the face of God. I was a big drama queen back when I was like 13 or something. So I've seen the face of, because this to me is a magical thing. It's by writing a sentence, you constrain an infinite number of points to behave in a linear fashion. Is that either? That's magic. No? All right, work with me. It's magic. And I had that same revelation when I learned calculus. Oh my God, we have the infinite again being constrained with a simple dx over. I mean, it's amazing. Anyway. So you recall that in the straight line equation, the m is the slope or gradient, and the b is the y-intercept. So similarly, right, that's what it looks like. So the y-intercept is where it crosses the y-axis. I'll review stuff. The m, the slope, is just a change in y divided by the change in x. I'll review. Yeah, good. Okay, excellent. So you can, here's an example of change of y is 2, the change in x is 1. The slope is going to be 2 over 1 or 2. The b is where you cross the line right there. So he's plugging the numbers, y equals 2x plus 1. All grade 10 stuff. Hopefully that's all review. That's why I'm going so fast. Good. All right, excellent. We don't use y equals mx plus b in statistics. We use y equals alpha plus beta x, but it means the same thing. So the alpha is the y-intercept, what used to be the b, and the beta is the slope. You may ask, why? Why do we change things up like that? And the reason is because we go beyond this to add more terms, different additional betas and additional alphas, and so forth. Now the textbook, because they're being problematic, uses a to bx. A instead of alpha and b instead of beta, but they mean the same thing. Classically, we use alpha and beta. It doesn't really matter. Right. Now, again, the single straight line, the single version, the simple version is just a special case of the multiple version. Okay? So when we say this is a linear equation, this is a multiple linear regression, it looks like more than just a linear straight line equation. That's a straight line equation. It's all this stuff. We still say this is a linear expression. Do you know why this is a linear equation, linear expression? Yeah? Order of 1. That is correct. Good job. All right. What does that mean? Yes, that is correct. You're not doing quadratic. So the exponents of the x's are just 1. There's no 2s, no 3s, etc. If there's a 2 there, anywhere, it would be a quadratic equation. If there's 3 there, it would be something else, be a cubic one, 4 would be a quartic, and so forth. It's the exponents on the x that matter. So I can add as many x's as I want here. It's still linear. And there are different kinds of x's. These are not the same x's. These are factors that are playing in here, so I can't add them together. But they're still linear. So in mathematics, linear just means the variables that we're dealing with are not squared or cubed or anything, just to the exponent line. So don't be confused. If we say linear, it doesn't mean a simple linear. It can be really complicated linear. If it's quadratic, then at least one of these would have a square on it, probably more than one. That's what the terms mean. Okay. So linear regression, we have a bunch of values for x, okay, and we're trying to figure out the best values for the alpha and the beta to make the equation such that we get a y equals a plus bx that has the closest possible fit. And that's really the kicker here. What does closest possible fit mean? ultimately, when I make this equation, I'm going to approximate the relationship. I don't get a precise relationship. I get an approximate relationship. It is possible for any set of data that you give me, for any set of points, any set of relationships. Let's say last year's class. Here's the midterm marks, here's the final marks. Okay, I can plot a precise equation to explain the relationship between the final and the midterm for any set of data. It's called a Fourier transform. Not to scare you, but fancy math terms. Maybe you've seen in your other math classes something called a power series transform. Power series and Fourier do the same thing. I can write all kinds of incredibly complicated equations to perfectly describe the relationship between two sets of variables. But it's not useful, right? Because even though I can perfectly predict last year's exam via last year's midterm, because I know what they are, the equation I make from that experience must be applicable to you as well. So I don't want to make it so incredibly precise and complicated that it no longer has validity in the real world. We call that external validity. Okay? That's why we're assuming it's more simple than that. And even though this is an approximation, it allows us to have a little bit of wiggle room because you guys are not the people from last year. So let's see how that works. So a straight line is that equation. And notice that the x here is italicized because the textbook uses the italics for the actual data points. See how that becomes clear later on. So this is the y value is one variable, x value is the variable, intercept, and so forth. We covered that already. The prime is a predicted value. So now we're going to predict values of y based upon actual values of x. So for example, maybe the x are the values of your midterm exam. Y primes be the predicted values of your final. Okay. We should actually do this. Do this for real. I'll do it for you in the next couple of days, and I'll make the equation and have you guys make it. To do that, you have to have each other's data. Can't allow that. I'll think of a way to see, in fact, that your actual final exam performance is as predicted. Hilarious and depressing. Hilarious and depressing at the same time. Okay, so the slope here is called the regression coefficient. That's what that thing is called. And when we do multiple version, it'll take on a different meaning. But be aware that these terms are changing. When we solve for alpha and beta to make our equation, we're going to use all kinds of things that we've done already. We're going to have deviations to the means, we're going to compute means. We have this thing called cross products, which are just, in the case of simple regression, are just multiplications. Cross products, have you heard that term cross products before in school math? Yeah, maybe. Cross product is a vector function. So it's a multi-dimensional multiplication process. Don't worry about it. We don't deal with that in simple regression. In the case of this example, it's just a multiplication. But we're using that term cross product specifically because when you move on to higher dimensions, it means something more than just multiplication. Higher dimensions, excited now, right? Sounds cool. Right, example. I want to predict your performance on the final exam based upon what you got on the midterm, as we will do. Right? So I want to be able to make a prediction for each of you. I want to make an equation, which is my model, such that if I plug in your midterm mark, I get a prediction for your final. If I plug in your midterm mark, I get a prediction for your final, and so forth. That's what we want to do here. To do this, we're going to make a model, right, which I can plug in the midterm marks and get a final. And the model is just the equation. How do we construct a model? To make any kind of model, whether it's statistical or humanities-based or conceptual, what we need is sample data. So sample data allows us to have a simulation of the relationship between the two sets of experiences. And I apply your experience to that simulation. So our sample data is based upon last year's class. Let's say, this is not last year's class, by the way, this is hypothetical. Let's say last year there are 10 students. And let's say this was their midterm mark for some reason out of 10. I don't know why I chose that. Let's say it's out of 10. And this is their final exam mark. Now, like I said, I can do all kinds of mathematical acrobatics to force a relationship between these two sets of data such that I get precisely 3 every time I plug in 2, and such as I get precisely 8 every time I plug in 9, and so forth. But simply getting a precise mathematical machine to get exactly that when I plug in that is not useful once I go beyond the context of these sets of data. I have to make it useful for when I get to your data. and elsewhere. So that's my data right now. How do I know what shape to make it? Obviously, we're going to do linear regression today, so we're going to assume it's a straight line. But it might not be. If I go back here, maybe plot this versus that, and we'll get like a curve and a quadratic equation, which is parabola. Maybe we'll get like a sine wave or something. Who knows? So the first thing I'm going to do is I'm going to graph it, because it could be a parabola, it could be monotonic, it could be a straight line. So here's a graph. Look at that. So this is the midterm marks, the final marks. That looks like a straight line, I think you'll agree. It might not be. We could argue that it's something else, but it looks fairly straight line-ish. And again, I'll say it again, using the Fourier transform or one of these more exotic techniques, I could create a curve that goes through every single line, like that, precisely. But who gives it? It's not useful. Right? Precision may not be usefulness. So linear regression is about being useful. So I'm going to assume there's a line here. Now, I can draw a line a variety of ways. This way, even like that way. The question is, which line do I draw? That's what linear regression allows us to do. It computes a line that is the most reasonable. And there are various ways of figuring out what reasonableness is. Okay? And the technique we're going to use is called the least squares method. Let's go through these. All right? So the outcome here is the y-axis and so forth. So here is the line we're going to plot. It looks reasonable, but again, I could have put it over here. And here, notice the y-intercept is down here. I could have had one going through the origin. Right? Why did I choose that line? Interesting. So we're going to try to get that line using this equation. And so I can plug in any x and get any y final. And how do I know which line to draw? Well, the method we're going to use is called the method of least squares. And this is what Gauss and Legendre stumbled upon, the least squares method. And it comes down to this. Here is the data points. Here are the points. Here is a hypothetical line I'm going to use to fit them. Notice each of the data points has a distance from the line. There are different ways I could have drawn that distance. I could have drawn the distance horizontally. Perpendicularly, I could have drawn it as well. Okay? Here, I've drawn it vertically. And that's the technique we're going to use. We're going to use a vertical line technique. I'm going to figure out a way such that the average distance between all these points and the line is minimized. Now, remember, this point here is positively above the line. This point here is negatively below the line. So that's going to be a negative measure, be a positive measure. How do I get rid of negative numbers? I square them. We've been doing that all along, right? I square them. So I'm going to add up all the squares and figure out which one has least sum. So the method least squares, that's all that means. It's not fancy at all. It's really basically grade 3 arithmetic stuff. But again, it was miraculously genius when Legendre and Gauss stumbled upon it. So I'll say it again. The least squares method is the way by which the vertical distance from each point to our hypothetical line squared, their sum is minimized. That sentence makes no sense. I know there's no verb or anything in there, but you get the idea. Okay? Again, I could have done it. Maybe it makes more sense to do a perpendicular line and minimize it that way. Absolutely, we could do it that way too. That's not the technique we're going to use, and that's not the technique that's typical. Yes. Okay, so if I add up all these distances, I get a number. If I move this line this way over here, let's say, and I recompute, I add up the new distances, it will be different. So our technique runs through a large number of scenarios and figures out which one gives me the least sum. Remember, calculus is all about figuring out which slope gives you 0, that kind of stuff. Right? It's similar without using calculus. Similar. Right. So this is how we're going to do it. We have our data again. Here is a number of data. Here is the midterm mark for each student. Here's the final mark. The first thing we're going to do is compute the totals and averages. The average midterm is 5. The average final is 6. Then I have my each data point minus the average. Right? I get that. Then I square them. I get that. Over here, I have y minus the averages, and I square these. Oh, sorry, I take the y multiplied by the x. Okay, I get that. All right, so now I just have these two numbers here, the sums, 68 and 61. What do I do with that? I plug in this formula, and I get 0.9. That is now my beta. I'm not going to in depth because it's just following the recipe. You can go through the recipe yourself. Add up all the xy, divided by all the x squareds, and you get 0.9. That's our estimate for the y-intercept. Now to get that's our estimate for the correlation coefficient. To calculate the y-intercept, we're going to take the average y and the average x and plug it into the formula here. Y minus b times average x, and we get 1.5. So that's our whole equation now. Simple, straightforward. What does that mean? That means for every midterm mark I plug into here, I'm going to get a prediction for the final mark. That works for that model. Because it works for that model, we'll assume it works for the next class as well. Again, that's hypothetical data. We'll do the real thing for your data and see how it turns out. Okay, so the final exam mark is 1.5 plus 0.9 times the midterm mark. That's the slope, that's the y-intercept. And it only works because I'm assuming that this relationship is linear, it's a straight line. And according to our scatter plot, it was a straight line. And many things are linear in the world. That's why it's so useful. So if I have a student who got 6.5 out of 10 in midterm, I can predict how he will do on that final. 7.35. Straightforward. So it's a quick and neat method of doing straight line, but are there issues with robustness? What do I mean by robustness? Robustness is, are there perturbations that can throw off the model entirely? Are there issues here that with their variable will make everything nonsensical? Obviously the answer is going to be yes. And I'll give you the example of something called Anscombe's quartet. I don't need you to memorize Anscombe's quartet. Don't worry about that. It's just here again for your edification. Anscombe's quartet is a theoretical collection of 4 different data sets, each of them having the same characteristics, but they're different data. Right? 4 cases of different data. In each case, the mean of the x is 9. In each, the variance of the x is exactly 11. In each case, the mean of the y is exactly 7.5. The variance of the y in each case is very, very close to 4.1. The correlation x and y in each place is very, very high, 0.81. And the linear regression for both of those cases gives us the same equation. So if I were to plot that line for each of these data sets, I would get exactly the same line. Great, right? Except if you look at the actual data, right? Here's what the actual data sets are on this quartet, and plot them. Right? So the first data set is that. This is the data, and our equation, our technique, our least squares method, gives us that line. Looks reasonable. The same line, though, also describes that data set. Clearly, there's something else going on here. That would be a curvilinear relationship. So that same line, different data, right? Another data point. That's same set of data, same line, different data set. So again, 1, 2, 3, 6, same line, all describes different data sets. So it's not robust to outliers. Right? So if I took out an outlier, the best line would probably be over here. Wouldn't be this one. This outlier drags it over here. And same over here. These outliers over here drag my line a certain way. If I took out these 3 guys, my line would be over there. So it is not robust to outliers and to very strange distribution. And this is the last of Anscombe's quartet. That's bizarre, isn't it? Again, if you plug in these instances into your straight line generator, you get the same line. That guy is dragging. If that guy was out, the line would look like this, right? If that drags everything that way such that I get the same line. You see the point. Is what we're doing here is estimating the best we can a linear relationship. But sometimes the relationship is not linear, and we forced it to be that way. Which is why I started out this by doing a scatter plot to show that it likely is linear. Sometimes it isn't. Right? So clearly outliers have a dramatic effect on the final linear model. That's why we like to check the data first to remove the extreme outliers so that things look as linear as possible. And we need some diagnoses, some diagnostic techniques to determine whether or not our regression is a good regression. We'll do that next class. But in the meantime, to do this in SPSS, you can go to Analyze Regression Linear, and that's your quick and dirty class again. Sweet.